Hello and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be doing the second installment for the Miller effect examples, specifically talking about the high frequency model of the MOSFET and talking about these three different questions, where question one is which capacitors can we get rid of in these two models, this being the first model and this being the second model. The second question being which capacitors can be merged. And the third question being which capacitance experiences Miller's multiplication. If you want to go ahead and pause the video and see if you can answer these three questions for these two configurations, please go ahead and do so. And then you can come back to the end of the video and see if you got the right answer. Where again, this is a common source amplifier, where the second one is a MOSFET Cascoded amplifier, or an MCA. Now, before we dive into the three questions being asked, we want to talk about where these capacitors are generated from in the MOSFET transistor. And in order to do that, we need to understand the high frequency model of a MOSFET. So similarly to part one of this example series, I'm going to draw out the cross-sectional model or layout for the MOSFET transistor. And essentially how that looks like is you have this gate and it's connected to a metal. And underneath it, you have this gate oxide or a silicon dioxide. I'll draw that last, but then you have the source terminal and you also have the drain terminal. Again, these gate oxide is somewhere here. All right. And it's an insulator essentially. And then these wells are built up on top of a P substrate, where these are lightly doped with electrons, or they have free holes. So I'm going to say that this is E pluses. All right. And this is my N channel. So N plus, N plus. And these are doped with electrons, or heavily doped with electrons. To understand quickly the working principle of the MOSFET, I'm going to redraw this image to the right-hand side and show how that works. So essentially, how a MOSFET works is when we connect the gate to a battery supply, you can imagine that I get a whole bunch of holes or positively charged electrons coming in and settling at the plate of the gate. It pushes these away. Okay, so these go away or they get rejected. So now they're on the bottom here. And there's a little bit of some electrons that are in the P substrate. They get attracted because there's an electric field right here. Okay, so it's attracting the electrons in the P substrate. And what actually happens is a well is created. Again, this is just a high level depiction of what happens in a MOSFET, but essentially this is what's going on. I hope that makes sense on a high level. If you have any questions about that, please let me know down in the comment sections below, and I'll be sure to get back to you. Okay, so now where do these capacitors come from? So let me go ahead and redraw a clean, nice new symbol. So let me see. This is my gate. It's connected to a metal. So this is metal. There is a insulator here. We call this SiOX2, or silicon dioxide. And this is my source. This is my drain. And the well goes a little bit, it overlaps with the silicon dioxide on both sides. The N plus, they're doped N type. and this is my P substrate. Okay, so we know that every time we have an N and a P intersecting, there's what's called a depletion region, okay, or PN junction. All right, so there's two PN junctions on either side here, PN. And whenever time we have a PN junction, we have a capacitance, right? A parasitic capacitance. So this is a CSB, right? Capacitance from the source to the bulk. This is also called capacitance from the source to the substrate. I will use CSB more often. And over here, this PN junction creates a parasitic capacitance. So we call this CSB or CDS. Okay, now the last two capacitors that are created are a result of the MOSFET, or how the MOSFET is made. So there's a capacitor here, right? Because there's a metal here, okay? And there is some insulator here, right? And this is P-doped, P-typed. So there is a capacitor there. So we call this the capacitor from gate to source. And this one we call the capacitor from gate to drain. So that's it for all my capacitors. Let me just clean it up with a nice small signal model. And so I'm just cleaning it up with a small signal model. And I'm going to say that if I have my gate, this is plus or minus V1. This is my source. It's a voltage controlled current source. So GM V1. This is RO. And this is my drain. So at the source, I have this capacitor here, this parasitic capacitor. So this is CSB. Over here, we then get CDB. Over here, we get C gate to source. And over here, we then just get CGD. So this is the relatively complete high frequency model for the MOSFET. Again, the reason why we want to consider this is because these parasitic capacitances and capacitors affect how the transistor behaves as we vary our frequencies from low frequencies to high frequencies, right? And again, that affects things like our bandwidth or our cutoff frequencies, right? So we want to be able to understand these capacitors, and we want to know how to evaluate our circuits with these capacitors involved. So now that we know where our capacitors stem from, let's go ahead and dive into the two examples we had from before. Okay, so the first example, or for the first example, the first question asks us, which capacitor can we get rid of? And in this situation, you can notice that we can get rid of CSB. So we can get rid of CSB. Why? The reason why is because on both sides, right, it's connected to ground, right? So we can get rid of it. Okay, so the next question is, which capacitors can we merge? And remember, merging means that a capacitor or two capacitors that are in parallel can be merged by adding them up. And what I'll do is I'll post a link to my capacitors in parallel video that I've made in the past on the top right hand side of this video. So please feel free to check that out. Okay, so from our Miller multiplier, Miller effect video, all right, we said that which capacitor experiences Miller effect. Okay, and in this situation, we see that it's going to be my CGD capacitor, and that's because at both ends of its terminals, it's connected to voltages, right? V in and V out. Okay, let's go ahead and redraw this circuit, take into account that CGD experiences Miller's effect. So then what we're looking at here is VDD, RD, my transistor, V in and V out. Again, at my V in terminal, I'm going to have a capacitor CGS, this one here. I'm going to have another capacitor CGD, and Miller multiplication requires that this be multiplied by 1 minus AV. And then on my output, I'm going to have this capacitor here, CDB, and this capacitor here, CGD 1 minus 1 over AV. From my video that I did with common source, we found out that AV is approximately minus GMRD for a common source amplifier. So again, we can go ahead and plug this in for AV, okay? And we can go ahead and combine these because they're in parallel, right? So let's go ahead and do that over here to the right-hand side. So I'm going to call this my final circuit approximation, where again, this is VD, RD, V in, V out, and this just becomes CGS plus CGD 1 or plus GMRD. Okay, I hope that makes sense. And over here, we get a capacitor CDB plus CGD 1 plus 1 over GMRD. Okay, I hope that makes sense. Again, the reason for us doing this is so that we can simplify our analysis when we're doing the frequency response of these circuits or of this amplifier, okay? If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. Okay, so for the second example, we consider again the 3 questions. So the first question being, what capacitor or capacitors can we get rid of? And in this situation, we can only get rid of CSB1, or this capacitor here, again, because it's connected to ground on both sides. So CSB1. So then the next question is, which capacitor can we merge? All right. And in this situation, there's a couple that we can merge. The first being these two right here. Okay. Because again, remember, VB is biased in AC, so it's simply just grounded. And then we notice that CGD2, this capacitor, and this capacitor are both connected both to V out and ground. So let me go ahead and write that out. So we can merge CGD2 and CDB2, which just becomes CGD2 plus CDB2. The next capacitors that we can merge, as you can see, will be CGS2, CDB1, and CSB2. So the one I just circled. So again, this makes up a merging of 3 capacitors, and I'm just going to write that out here. This becomes CGS2 plus CSB2 plus CDB1. Okay, so the last question is going to be, which capacitor experiences Miller's effect? And again, as we can see, only CGD1 right here is affected by it because it's connected to both Vin and this output voltage here. Let me call this V1, okay, on either end. So then the answer to this is CGD1. And because it is connected to Vin, this is CGD1, and this is my voltage V1. Okay, so what I'm going to do now is I'm just going to write out the final circuit approximation, similar to how I did on the previous example. So this is simply just, so we get VDD, RD, my two transistors, M1 and M2. We get a V out. We get a VB, but this is just grounded in AC. All right. And we get a VN. So then over here, we get two capacitors added to one another, which being CGS1, which again is this capacitor right here, plus CGD1, 1 minus AV, right? It's the capacitor that experiences Miller's effect times the Miller's multiplication, which is 1 minus AV. All right. At this node V1, we have two capacitors, or we have a bunch of capacitors. It's going to be these three capacitors merged together. So I get CGS2 plus CSB2 plus CDB1. And then lastly, the Miller capacitor that is being multiplied by the Miller multiplication. So CGD1 times 1 minus 1 over AV. And then over at V out, I simply get my this capacitor here. Okay, so then that becomes CGD2 plus CDB2. So now the only thing to do is describe what this AV is. And again, I did a video proving this. The video is called Cascoded Amplifier Part 2. So we can say where AV is approximately minus GM1 times 1 plus GM2 RO2 RO1 plus RO2 in parallel with RD. Okay, and essentially this is approximately minus GM1, or the transconductance of this transistor, times RD. Okay. Again, I've posted the video to this on the top right-hand side of the corner of this video, so please feel free to check that out. If you have any questions on any of the examples we did here, please leave them down in the comment section below, and I'll be sure to get back to you. If you like the video, please give it a thumbs up. And if you like what the YouTube channel is providing, please feel free to subscribe. Thank you.